All right, now what this video is going to be about is it's going to be about solving yet more problems in the field of magnetism. So we're going to be solving 4 problems today, and let's get started. So the first one says we have a square current loop who's 5 centimeters by 5 centimeters on each side. It's going to carry a current of 500 milliamps. The loop is in a 1.2 Tesla uniform magnetic field. The axis of the loop is 30 degrees away from the direction of the field. What is the magnetic moment and the magnitude of the torque on the current loop? So we're going to be looking for the magnetic moment. The equation for magnetic moment, or the symbol for magnetic moment, is mu, and it's going to be N-I-A, where N is the number of coils, or the number of turns. In this case, we only have one. I is going to be the current, and A is going to be the area. Now we can write this as N-I, and then we could have it length times the width, where L is going to be the length and W is going to be the width. And this will be equal to, now remember, we have one turn or one coil, so that's going to be 1. Our current is going to be 500 times 10 to the minus 3 amperes, because we convert from milli to amps. The length is going to be 0.05 meters times 0.05 meters. So all I've simply done is I've converted the centimeters into meters. If we go through and do this arithmetic, we will end up getting 1.25 times 10 to the negative 3rd amp meter squared is going to be our magnetic moment. Now, if we're looking for the torque, our torque is going to be equal to the magnitude of the cross product of mu cross B. That's equal to mu B sine phi. We already just found what mu is. Mu is going to be 1.25 times 10 to the minus 3rd amp meter squared times our magnetic field, which is 1.2 Tesla, times, now the sine of our angle is going to be 30 degrees. So it'll be the sine of 30 degrees. We go through and do this arithmetic, and we will end up getting 7.5 times 10 to the negative 4th, and this becomes Newton meter is going to be our units. And so that's going to be our torque. Remember, torque is always going to have units of Newton for a force and a distance. All right? And yet we have another problem here dealing with magnetism. And this one says the 1100 turn coil in a DC motor has an area turn of 1.2 times 10 to the negative 2nd meters squared. The design for the motor specifies that the magnitude of the maximum torque when the coil is placed in 0.25 Tesla field. What is the current in the coil? So we're looking for current. Now if we go to our equation for torque, that is going to be equal to N, which is the number of turns. A is going to be the area. I is the current. And B is for the magnetic field. If we solve this for I, that is going to be equal to tau, the torque, divided by N, the number of turns, divided by the area, divided by the magnetic field. And so we can now plug all this in, and this is going to be 6.2 Newton meter divided by 1,100 turns, which is just going to be a number, time, we're going to leave the units out. The area, which is 1.2 times 10 to the negative 2nd meters squared, times now the magnetic field, which is 0.25 Tesla. We do the arithmetic here, and we end up getting 1.89 amperes. Or we can say that's approximately equal to 1.9 amps. And so the current that this electric motor is going to draw will be 1.9 amps. The problem we have next reads as following. A long straight wire carries a current of 48 amps and has a magnetic field at a certain point of 8.0 times 10 to the negative fifth Tesla. How far is the point from the wire? Well, we can look at the equation for the magnetic field that is generated from the current within a wire, and that's going to be mu naught I all upon 2 pi r. And what we're going to be solving for here is we're going to be solving for the radius. And so the radius, I'll write it right here. Radius is going to be equal to mu naught I upon 2 pi b, which is equal to 4 pi times 10 to the negative seventh. That's going to be mu naught. That's the permeability of free space. T times m divided by A times our current, which is 48 amps, all upon twice pi times B, which is 8.0 times 10 to the negative fifth of a Tesla. And so you can see the units how it cancels. Tesla will cancel with a Tesla, amp will cancel with an amp, and we're going to be left in units of meters. We go through and do this arithmetic, and we find out it's going to be equal to 0.12 meter. All right? Now what we're going to be dealing with is going to be dealing with a problem about a solenoid. All right? Remember, a solenoid is going to be a tube with a bunch of wire wrapped around it. As you pass a current through it, it's going to generate a magnetic field. And so a solenoid is wound with 1,400 turns and has a length of 0.65 meters. If a 4.7 ampere current passes through a solenoid, what is the magnetic field strength? So for that, our equation is going to be B is equal to mu naught I lowercase n. Remember, the lowercase n is the number of turns per length. I is the current, mu is going to be the permeability of free space. So this becomes equal to mu I and capital N, the number of turns, divided by our length. So we put the naught in there. So if we put these numbers in, we have 4 pi times 10 to the negative seventh, and this is going to be a Tesla meter per ampere, times our current, which is 4.7 amperes, times the number of turns, which is 1,400, divided by our length, which is 0.65 meters. All right? So our meters cancel with our meters, our amperes cancel with our amperes, and we're in units of Tesla. We do this arithmetic, we end up getting 0.127 Tesla. All right? If you have any questions on this chapter, you are more than welcome to ask them to me. Thank you.